In this video, we're going to learn how to calculate the change in entropy in a chemical reaction. So far, our work with entropy has been concentrated on learning how to calculate changes in entropy for simple processes like heat and cooling, gas expansions, and phase transitions. Now we're going to take that knowledge and proceed further to try to see if we can tackle here chemical reactions. So think of a generic chemical reaction of reagents to products. Our goal is to simply calculate what the change in entropy is going to be. Alright, so this is a chemical reaction. The way that we're going to write this is change in entropy for the chemical reaction. We're generally going to be interested in molar quantities, so this will be joules per Kelvin per mole. And then we're also generally going to be interested in the standard state, that is pure substances with 1 bar pressures. Now the question is, how do we compute this quantity? Here we can draw inspiration from what we did with a different state function, which was the enthalpy. And in the enthalpy, what we simply said is that if you have a knowledge of the enthalpy of products and a knowledge of the enthalpy of reagents, you simply take the difference between those two. And because enthalpy is a state function, then that means that the only thing that matters to compute a change to the state function is what is the final state, products, what is the initial state, reagents, and that's it. Okay, so for entropy, we're going to do exactly the same thing. We're going to say, well, the change in entropy in a chemical reaction is simply going to be a measure of the entropy of your products, okay, entropy of products, which will be molar and then standard, and then a measure of the entropy of reagents, molar and standard. Okay. Now the question is, well, what are these measures of the entropies of products and reagents? Okay. Well, when we were actually working with enthalpies, then what we said is that there's no way to generally know what the absolute enthalpy of a substance is, and because that is true, or that is the case, then we actually had to come up with an arbitrary scale to which or with which we could calculate what enthalpies were on that scale, and that was the enthalpies of formation scale. We simply set the zero arbitrarily at the most stable allotropes of elements, and then we simply just referred the enthalpies of any substance to that sea level to obtain enthalpies of formation. Now the question is whether we have to do the same thing here for our molar entropies, and the answer is no. For the molar entropies, we can have a knowledge of what the absolute molar entropy of a substance is. Now, how do we actually determine those absolute molar entropies is going to be part of the next video, which deals with the third law. Okay, but for now, suffice it to say that again, we can actually still use this recipe. Okay, but then we will be using absolute molar entropies for substances and not entropies of formation, much as what we did with the enthalpies. Okay, so just to complete this a little bit more, suppose that you have a generic chemical reaction, A plus B to give C plus D. Now, for this chemical reaction, then what you have to do is you simply add all of the absolute molar entropies of your product species and then multiply by the stoichiometric coefficients. That's what this new letter is. And then subtract is the sum of the molar entropies of all of the reagent species multiplied by the stoichiometric coefficient. Okay, and again, those are generally going to be all standard and molar. Okay, so hopefully this video has shown you how simple it really is to calculate the change in entropy in a chemical reaction if you have absolute molar entropies for reagents and products. In the next video, where we handle the third law, we're going to learn exactly how to calculate those absolute molar entropies for substances that can be conveniently used to obtain the change in entropy in a chemical reaction.